Hello, welcome back to my channel. Part 3 of the semester exam review. I'm going to be covering Unit 9, Stoichiometry. So that covers the mole conversions, limiting reactant, empirical, and molecular formula. So lots of math today. So make sure you have your calculator, periodic table, all that stuff, and hopefully you can do some problems with me. The first thing we're going to do is the mole mass conversions. And on the final, there's pretty much going to be like one of each type. So first we're going to do mole to mole. And I'm just going to start off with a balanced equation. And I'm going to leave this as 1, just so you know the coefficient is 1 here. And we're going to use this equation for all the mole conversion example problems. So as a reminder, these numbers here, the coefficients tell you the mole ratio. So coefficient equals number of moles of each compound. So for example, I have 2H2. That means I have 2 moles H2 for every 1 mole O2 for every 2 mole H2O. And it doesn't matter how complex or how simple the reaction is. So the coefficients, no matter what, tell you how many moles of each. Alright, so let's start off with the first example. How many moles of H2O is produced if 13.7 moles O2 is used. So this is a mole to mole conversion, so this is a 1-step. Alright, so when you read the question, I would underline what you're given. And that's what you're starting off with. You do your little train track here. And then I would box what I need to find. This is my unknown. This is my end goal. Alright, so let me zoom out just a little bit. Always write your units in your train track so it tells you what to do next. So I have mole of O2. I'm going to move that diagonally, and by moving it, it's just the units. Do not copy down the number. So mole of O2 here, move it down here, mole of O2. Alright, and since I'm looking for H2O, I'm going to do mole H2O on top. That's always our goal. Our goal always goes on top. Whenever we have mole to mole, that's when we look at our mole ratio. So according to the equation, I have 2 moles of H2O, and I have 1 mole of O2. Now the setup is done. We just solve right now. So I have 13.6. So this is like a ratio. So numbers next to each other you multiply, then divide by the bottom. So this is pretty simple. It's just 13.7 times 2 divided by 1, which is just 13.7 times 2. That is 27.4 moles of H2O. Okay? So that's a mole to mole example. Let me give you another one mole to mole, and you're going to try this by yourself. How many moles H2 is needed if 5.4 mole O2 is used? Alright, so go ahead and pause this video, try it out, and let me actually pull the equation up here so you can see the equation right there. Alright, so pause the video, try it out, and then play once you get your answer to check your work. Alright, so you should have gotten 10.8 moles of H2. So I start with 5.4 mole O2, put the mole O2 here, and then I'm looking for moles H2, and then the ratio is 2 to 1. When I solve, it's 5.4 times 2, which is 10.8. Okay, so let's do another type of conversion. Okay, how many grams H2O produced if 10 moles of O2 is used? So this is a mole to gram conversion, or mole to mass conversion. So same idea. You're starting off with 10 moles of O2. Then we look at our units, mole of O2, pull it down, mole O2. And so this is where you got to be careful with the grams. You can't go directly to grams of your wanted. You have to go to your moles of your wanted first. So I'm going to put mole H2O. Again, I call this the heart. Pretend this is like the heart here, because we got to go to the heart before we go to anywhere else. So I'm going through the mole first. That is a terrible heart. Like that. That's the best I could do. So think about, the blood in your body. It always pumps through the heart before it gets to, your brain or your lungs, anywhere it needs to go. Always goes to the heart. So same thing with chemistry. You always go to the mole to wherever you need to go. So now that we have our mole to mole, we use our mole ratios here. I have 1 mole O2 and then 2 moles H2O. And then we keep on going where we need to find grams. Now we do mole of H2O. Pull that down here, mole H2O. Alright, and then we are looking for grams, so that goes on top. And then grams of anything comes from the periodic table, so that's when you take your mass of your hydrogen times 2, and then plus your mass of your oxygen. So like 2 times 1.008 plus 15.999. Just to save you the time, get 18.015, and then the grams of anything is always over 1 mole. That means for every 1 mole of water of H2O weighs this much, 18.015. And from there we solve. So 10 times 2 times 18.015, and then divided by, in this case it's 1. So 10 times 2 times 18.015. This is going to be a large number. I got 360.3 grams of H2O. That is your final answer. Alright, so the last type of mole conversion I want to cover is mass to mass. So let's say I do how many grams of H2 is used to produce (15 grams of water. Alright, so we are starting with 15 grams of water. And again, this is a gram to gram, or mass to mass. So this is the longest train tracks that you're going to do. Same idea. We're going to do our grams of H2O. Pull it down here. Grams of H2O. Again, grams of anything comes from the periodic table, which we just found here, 18.015. and then the other side has to be 1 mole, hence the molar mass. And then you keep on going. So now we need to get to grams of H2, but again, we need to get to the moles first. We got to go through the heart like this one. So mole of H2O, pull it down here, mole H2O, and then we want mole H2 first. And then we look at our mole ratios. So in this case, it is 2 moles H2, 2 moles H2O. So that makes things easier because they're eventually going to cancel each other out. And then one last step here, since we want grams, I do mole H2, pull it down here, mole H2, and then grams H2. Alright? So grams of H2 comes from the periodic table, so 2 times the molar mass of H, so that'll be 2.016, and the other side is always 1. And from there, we solve. So I'm just going to go ahead and just cancel out the 2's since they're on the opposite side. So I'm just going to do 15 times 2, 15 times 2.016, that divided by 18.015, making the math easier. I got 1.68 grams H2. Okay. So that's pretty much the mole conversions. The next thing on the stoichiometry list is the limiting reactant. Now, I'm going to go simple with the limiting reactant. It's not too deep on the final. Basically, instead of doing chemical reactions with limiting reactant, you're going to have like a recipe for something. So let's say I'm going to give you a recipe. First title it limiting reactant. Reactant. There we go. So what is limiting reactant? Again, so limiting reactant, I'm going to abbreviate to LR, is the reactant that runs out first in a reaction. RxN for reaction. And then you have, when there's a limiting reactant, there's an excess reactant. So that's reactant, that's obviously excess. That's left over. So think about making s'mores, making a sandwich, and you run out of an ingredient first. That basically forces you to stop making that ingredient. So let's say I have to make one sandwich. So one sandwich equals 2 breads, so 2 pieces of breads, plus 1 salami, like 1 turkey slice, I don't know, 1 salami, 1 tomato, and 1 cheese. Alright? However, in your fridge, let's say your, I'm going to call it inventory. Let's say in your inventory, for you to make sandwiches, let's say I have 4 breads, 2 salamis, 2 tomatoes, and 1 cheese. So you can obviously kind of see what runs out first, right? So when we look at our ingredients here, you can see how many sandwiches I can make based on what I have left over. So with my 4 breads, I can make 2 sandwiches. with my 2 salamis, I can also make 2 sandwiches. So far, so good. My 2 tomatoes, I can make 2 sandwiches. Alright, I have only 1 cheese, and I can only make 1 sandwich with this 1 cheese. So which one would be my limiting reactant? It would have to be the cheese. Because once I run out of the cheese, I'm basically stumped. I can't make any more sandwiches. I have these extra ingredients left, but I can't make a full sandwich. Unless you want to make a sandwich without a cheese, you know? So that is basically how you solve for that when you have kind of a food situation, okay? Let me give you another one where, like, let's say you're making cake and you're going to figure out which one's your limiting reactant. Let's say I give you 1 cake recipe. Let's say that would be, need 2 eggs for it, 1 cup of flour, 1 cup of milk. What else do you use in a cake? Yeah, let's just do that. 2 eggs, 1 cup of flour, 1 cup of milk. But then your inventory, what you have left is the following. Let's say I have 3 eggs. Let's say I have 2 cups of flour. Oh, flour. I completely misspelled that. And I have 4 cups of milk. So go ahead and try to figure out, I would try to do it like this, unless you have another way of solving it, but try to figure out which one of these ingredients is the limiting reactant for you to prevent you to make like as many cakes as you can. So pause the video and then check your work once you're done. Alright, I hope you got eggs as your limiting reactant. So based on my ingredients, I can make a cake and a half. Not that it exists, but with 3 eggs you can make 1 full cake, and then you only have 1 egg left. So only 1.5 cake with the 3 eggs. You can make 2 cakes with the 2 cups of flour and 4 cakes with the 4 cups of milk. So what runs out first is the lowest number, so that would be the eggs. Pretty straightforward. Okay, so next thing on the list is the empirical and molecular formula, which is the last thing in the stoichiometry units. Alright, so the difference between empirical and molecular. So I'm just going to abbreviate EF. So that is the simplified version of a compound. So simplified formula. And then molecular formula is the unsimplified. So empirical formula is the one that has that special poem that we use. Solve poem. So when I give you a series of masses or percentages, there's like a poem to solve for the empirical formula. So hopefully it'll come back to you. So the poem is percent to mass, mass to mole, divide by small, round to whole. Alright, so let's just use this poem for our example. So find the empirical formula with 60% sulfur, and 40% oxygen. Alright, so the percent to mass, our first line of the poem. So percent to mass, always assume out of 100, which makes sense. So 60% out of 100 grams. So 60 grams of sulfur, 40 grams of oxygen. So 60% sulfur would be 60 grams of sulfur. 40% oxygen, 40 grams of oxygen. And honestly, you don't even have to do this part. Just change to grams, just literally change the units. Alright, mass to mole. So how do you do that? Again, you divide by the molar mass from the periodic table. So 60 grams divided by the molar mass of sulfur, 32.066. You get a number. We'll get that to in a second. Then oxygen, molar mass of oxygen, we all know it's, alright, 15.999. So let's get those numbers here. 60 divided by 32.0. 1.871, round to 3 decimal places. 40 divided by 15.999. 2.500. Alright. Divide by small. So you're going to look at between these two numbers which one's the smallest. So that's 1.871. So I'm going to divide each one by 1.87. And when you divide, that's when you round till the nearest whole number. So we're kind of doing these last two at the same time. So obviously 1.871 divided by itself is 1. 2.5 divided by 1.871. Go round to the nearest whole number. That's also 1. So that means I have one S and one O. That is your empirical formula. So the molecular formula for this, it can be S2O2, S4O4, whatever. So this is the simplified version of this compound. Let me give you another one, and you're going to try this by yourself. All right, find the empirical formula with 45% nitrogen, 15% oxygen, 40% fluorine. So go ahead and find this, pause the video, try it out, and check your work when you're done. Alright, this is what you should have gotten. It looks really weird, but that's pretty much the problem that I came up with. This is the empirical formula with the nitrogen, oxygen, and fluorine. Okay, so that is empirical formula. Next thing I want to cover is molecular formula. That's basically when you take your molar mass of your molecular formula divided by molar mass of your empirical formula. That would be your coefficient. And then you multiply it back to your empirical formula. So here's an example. Right, find the molecular formula. Okay, so find the molecular formula of CH3 if the molecular formula molar mass is 45.11 grams. So just as a reminder that the molar mass of the molecular formula here, it is always given to you. What you need to do is find the molar mass of your empirical formula, which is this one. So the empirical formula is always given. You find the molar mass of that, and then you basically divide this number divided by the number you just found. So first thing is find the empirical formula molar mass. So you have CH3. When you find the molar mass of that, you should have the carbon molar mass plus 3 of the hydrogen molar mass. So you should get 15.035 grams. So that's your molar mass of your empirical formula. And then you already have the molar mass of your molecular formula. So you do 45.11 divided by 15.035. And you round it to the nearest whole number so you get your coefficient. So when I do that, I got 3. So I'm going to plug that 3 back into CH3. That would be C3H6. I just unsimplified CH3, the molecular formula. Okay? Awesome. Alright, one last example. You're going to try this by yourself. And that would conclude today's video. Alright, try this out. Pause the video and then play once you get your answer to check your work. Alright, so the answer is C4H14. I found the mass of C2H7, which comes out to be 31.078. I divided it by 62.016, which gets me to the whole number 2. And I multiplied it back in to get C4H14. Okay, so I hope this helped. That's pretty much the entire Unit 9 Stoichiometry unit. I hope this helps. Let me know if you have any questions. But yeah, have a great day.